We also have I-type instructions. So similar to R-type instructions, these I-type or immediate type instructions have 3 operands, but now one of the operands is immediate. It's a 12-bit choose complement immediate. So we still have a destination register, RD, and a source register, RS1, but now we have one of our operands being an immediate and being coded as a 12-bit signed or choose complement immediate. And other fields, it still has an opcode, just like the R-type instruction. Actually, all instructions have an opcode. And funct3, this 3-bit function code that with the opcode together, they tell the computer what operation to perform. And so here's the format of this I-type instruction. We have our 12-bit signed immediate. Field comes first, RS1, and funct3, and RD. And then we have on the rightmost or the least significant bits is our 7-bit opcode. Here are some examples of I-type instructions. Here's the add immediate instruction that has a destination register, RD, a source register, RS1, and our immediate or signed immediate. In this case, the immediate is the number 12. And again, we convert those names to register numbers, X8 and X9. So here we have our RD field, 8, and we have our RS1 field, our source register, 9, and finally we have our immediate, in this case, it's 12. It's a 12-bit signed immediate, happens to be the number 12. And we have the opcode, in this case, 19 for the opcode, and funct3 of 0 indicate perform the add immediate operation on the operands. And again, we take these and we convert them into binary. 12, represent 12 as a 12-bit signed or choose complement number. RS1 as a 5-bit number to be able to indicate 32 registers. Funct3, 3 bits representation of 0. 8, 5-bit representation of 8. And 19, the 7-bit representation of 19. And we gather groups of 4 starting from the right. And we have, the rightmost digit is 3, and then 1, and so on, to get the 32-bit hexadecimal representation of that instruction. And we have other instructions. Here's a negative immediate. It's add immediate again, so the op and the function 3 or funct3 codes are the same. But now we have a negative number, negative 14, and you can tell this is the 12-bit representation of minus 14. That's a negative number just by looking at that sign bit. And turns out that these load instructions, load word, load half, and load byte, are also I-type format. They use the I-type format. So we have our source register, S3. We're going to use that as a source operand. That's register 19. And we're going to encode an immediate field. In this case, -6 is the offset. And then our destination where we're going to load that into is T2 or register 7, X7. And then our op and funct3 field, opcode and funct3 field, tell us that this is a load word. And you'll notice for the load instructions, the opcode is the same, is 3, 7-bit representation of 3, and 0 is load byte, 1 is load half, and 2 is load word for the function 3 or funct3 field. The SB type instruction is for, S stands for store and B stands for branch. And these differ only in the immediate encoding. That's why we group them together. So they both have an op code, well, like all instructions, a funct3 field, like the other instructions. And then we encode RS1, RS2, so 2 source operands. And then the immediate field. So the immediate field is where these differ. So we'll talk about this in detail, but the immediate field, is a 12-bit signed immediate for the store type instruction that's encoded, kind of in these two locations split up there. And then for the B type instruction, it's actually a 13-bit signed immediate, and the 0th bit is not encoded, and we'll talk about why. So the S type instruction, or store type instruction, has 3 operands, and you can guess this is used for store instructions like store word, store half, and store byte. And we have a base register, that's our RS1 field. That was the base register for our load word instruction too, RS1. And then RS2 is a second source, or the value that's going to be stored to memory. And we have our immediate field that is a 12-bit choose complement or signed immediate. And just like the other instructions, we have an opcode and a function 3 field as well. And so RS1 and RS2 are in the same location as in other instructions that include those fields, RS1 and RS2. And our opcode and function 3 fields are in the same bit locations of the instruction as other instructions that have those fields. And then the immediate is split between 2 kind of locations in the instruction, in the high bits and then in bits 11 to 7 of the instruction. So here's an example, some example S-type instructions. We have store word, store half, and store byte. And so, typically we don't have a negative offset, just to show that can be, it's a signed number, so that could be a negative offset. Here we have RS1, our base register, S3, or register number 19. So here's RS1. And then we have our second source, the value that we're going to store to memory. And so that's T2, or register 7. That's RS2. And then we have this immediate field -6, and the upper bits, so -6 is all ones and then 0, 1, 0. The upper bits, upper 7 bits, are stored in the upper bits of the instruction, and then the lower 5 bits are stored right next to the opcode, so lower in the instruction field, in the instruction bits. And similar format for the rest of these. So we have our source, RS1, we have our second source, the value that's going to be stored, or the register that holds the value that's going to be stored, in this case 20, and then our immediate field is split between, so 23, the higher bits, the high 7 bits of the address, and then 5 bits lower in the address. And again, we can, once we have the fields here, I wrote this part in binary already, just to show which bits are in each field. And then we can write the entire instruction in binary, 7, 19, 2, and 35 is the opcode used for those store instructions. And then gather groups of 4, starting from the right, to write it in hexadecimal. We have 3, and then 2, and then D, and so on until we gather all the groups of 4 and write it in hexadecimal. For the store instructions, you'll notice that the opcode is 35 for all of those, and then store byte is 0, store half is 1, and store word is 2 for the function 3 or func 3 bits. The B type instruction is similar to the S type instruction, so B stands for branch, the branch type instruction. It's used for branches. Has 2 source operands, RS1 and RS2, and has an immediate that's encoded in 12 bits of the instruction, but this time we're encoding a 13-bit choose complement immediate. This is the address offset. So this time, even though we're using only 12 bits of the instruction to encode it, we're actually encoding a 13-bit immediate. And we do this by not encoding, you'll notice this doesn't include bit 0 of the immediate. And we'll talk about why we can do that. So as before, we also have the opcode and the function 3 bits. So here we have RS1 and RS2 in the same locations as those those operands in other instructions. And we have our op code and our function 3 field, also in the same locations as other instructions. And then we split up our immediate like we did in the S-type instruction, but now we're using different bits, encoding different bits in those fields. But we have a 12-bit field separated into 2 locations in the instruction, 2-bit locations. But we're encoding a 13-bit immediate. And let's talk about how we do that, or why we do that. So here's an example B-type instruction. So remember, we're going to encode this 13-bit immediate in a 12-bit field. So the immediate encoding is strange, and the reason we do that is to keep the bit locations of certain bits of the immediate as consistent as possible. And we'll come back to that, talk about that later as well. But here's our branch equal instruction. And so this branch is branching to L1. And so we want to branch, in this case, 16 bytes later, or 1, 2, 3, 4 instructions after the branch. And so that's 4 times, so 4 instructions is past the current branch is where we want to branch to. So that's 4 times 4 bytes per instruction. 4 instruction times 4 bytes per instruction equals 16 bytes. We want to branch 16 bytes past the branch of equal instruction. And so our immediate, our 13-bit immediate, is going to be the number 16. So in this case, here we go, the 13-bit representation of 16, all zeros, and then a 1, 0, 0, 0, 0. But one thing we know is that we're going to branch a multiple of 4 past the current instruction because our instructions are 4 bytes, right? And so actually, we wouldn't need to encode either of those 2 bits, the lower 2 bits, because we know it's going to be zeros, right? So if we have our instruction addresses, if they were 0, 4, 8, C, 1, 0, they're all divisible by 4. So we have 0, 4, 8, C, 1, 0. So you'll notice, right, all of these lower 2 bits are always 0. But it turns out in RISC-V, only the least significant bit isn't encoded in bits. Why is that? That seems strange. Why not just not encode both of those? Well, it turns out that in RISC-V, compressed instruction or 16-bit instructions are used when possible. And so 16-bit instructions, which these are all 32-bit instructions, the ones we're talking about right now, 16-bit instructions would mean that the address would go, right, if we use 16-bit instructions, 0, 2, 4, 6, 8. So every 2 bytes, right, our instruction address would be divisible by 2, which would mean that only this least significant bit is guaranteed to be 0. Right, we have 0, 2, 4, 6, 8, ... right, 8, 10, 12. Okay, so for that reason, B-type instructions do not encode only the least significant bit 0 of the immediate. And then some very strange bit swizzling to encode our immediate. We encode bit 12, so bit 12 here is the most significant bit here, and then bits 10 through 5 are here. In fact, let's do that in a different color. So bit 12, this shows immediate bit 12, and then we have bits 10 through 5 in the upper kind of part of the immediate encoding. And then in the bottom part of the immediate encoding here in this field, this 5-bit encoding, we encode bits 4 to 1. So here are these bits. And then finally, we encode bit 11. So it's, you know, completely kind of annoying. But the reason that we're going to do this is actually to make the hardware design easier, and we'll come back to that point later. So just for now, notice that, well, first of all, we're going to encode a 13-bit immediate, but not encode bit 0, because it's always going to be 0. And then we're going to bit swizzle in this strange way and split across two fields our 13-bit immediate, except for bit 0. And again, this is a 13-bit signed or 2's complement immediate, so we can branch both forward, or we could also branch backwards. The UJ type instruction, or upper immediate type, is for the U type, and J type is for jump type. They differ, again, just like the SB type, only in how we encode the immediate. So in the U type instruction, we're going to encode a 20-bit upper immediate, so bits 31 to 12 of an immediate. And the J type instruction, we're going to encode a 21-bit immediate in a 20-bit field, right, in a 20-bit immediate field here. So we use 20 bits to encode a 21-bit immediate, and again, we do some strange bit swizzling of that 21-bit immediate. And how do we encode a 21-bit immediate in a 20-bit field? Again, we don't encode bit 0 of that immediate. So here's the upper immediate type, or U type instruction. It's used for load upper immediate, and we're going to encode 20 bits, upper 20 bits of a 32-bit immediate. So bits 31 to 12 of the upper immediate. And again, those lower bits we don't need to encode because they're zeros. And this instruction only includes an opcode, or a 7-bit opcode. There's no funct3 or funct7 field. So the opcode completely determines what operation to perform for U-type instructions. And then there's a destination field, RD. Again, we use 5 bits, and here's our immediate encoding. Again, that upper 20 bits of the immediate. Here's a U-type example, upper immediate. Here's the load upper immediate, or LUI instruction. RD is the destination register, and our immediate field is the upper 20 bits of that immediate. And so, for example, suppose we have load upper immediate, S5 is our destination register, or we convert that into the registered number, which is 21. And then we have our immediate, hex 8CDEF, and we put that in our 20-bit immediate field. And the opcode for load upper immediate is 55. We write that, all those fields in binary, and then we can gather groups of 4 and write it in hexadecimal. The J-type instruction, or jump type instruction, is used for the jump and link instruction, so JAL, and it has 2 operands, RD, and a 21-bit immediate. So we're only encoding 20 bits of that immediate. We're not encoding bit 0. Right? We're only encoding the bits 20 to bit 1. And like the U-type instruction, this includes only an opcode field, no funct3 or funct7 field. So RD is the destination, typically, right, our RA register, where we're writing PC plus 4. And then we do some strange, or RISC-V specifies some strange kind of bit swizzling for that 21-bit immediate, again, to keep those bits in the same instruction bit as possible across instructions. So one thing to note is jump and link register is not a J-type instruction. So jump and link register, JALR, and then we have our source register, where we want to jump to a register. This is not a J-type instruction. Turns out the JALR is actually an I-type instruction. So here we have a jump and link instruction, a J-type instruction. This is actually the only J-type instruction that we have in RISC-V. So here's the instruction, jump and link, RA func1. RA return address will get written with PC plus 4. And func1 indicates the location, or the address of the label. So in this case, ABC04. So in order to find out what we should encode in our immediate, in our 21-bit immediate, we find out the difference between PC. Remember that PC points to or holds the address of the current instruction. So when jump and link is executing, PC has the value hex 540C. And so in order to know where to jump to, we subtract the current address, so what's in PC, from the destination, in this case ABC04. And so we get our that difference, basically that offset. So eventually we're going to add, right, in hardware we'll add this A6, 7, F8 to the current PC to get what's called the target address or the jump target address. And once we add those together, then we're going to get hex ABC04, which is the destination or the target address. So we're going to encode this immediate into our immediate field. In this case, we have 20 bits. Just like branch for our J-type instructions for jump and link, here's our 21-bit immediate, but we're not going to encode that least significant bit. And so we encode all of the other bits 1 to 20 in our immediate field. And again, some strange bit swizzling here. Bit 20 goes in that most significant bit, and then 10 through 1. We have bits 10 through 1, and then bit 11, that bit, and then finally bits 19 through 12. And then we can write that, taking groups of 4, write that in hexadecimal. So we get hex 7 F8A 60EF. So again, a quick review of our instruction formats for RISC-V. We have R-type instructions, 3 register operands, with that strange exception where we use RS2 for the shift amount for shift immediate instructions, like shift right arithmetic immediate or shift left logical immediate. I-type instructions where we have RS1 and RD as register operands, but we also have this 12-bit signed or choose complement immediate. SMB type instructions where we have 2 source operands and an immediate for S-type instructions, 12-bit signed immediate. For B-type instructions, a 13-bit signed immediate with a strange bit swizzling of the immediate across these 2 bit fields in the instruction, and we don't encode bit 0. UJ-type instructions that have only a destination register and an opcode. They do not include func3 or func7. Only R-type includes func7. And U and J-type instructions for U-type instructions, a 20-bit upper immediate, so we only encode the upper bits of an immediate. And for J-type instruction, it's a 21-bit immediate encoded in a 20-bit field because we don't encode bit 0. So here's an example of design principle 4, which is good design demands good compromises. This is kind of the caveat of, well, we would have liked to have simplicity favors regularity, right? If we just had one format, that would be easier to deal with. Then our hardware just has to deal with one thing. It knows exactly where to find the operands and, the immediate. But multiple instruction formats allow us some flexibility. So add and subtract have 3 register operands, whereas other instructions like load word, add immediate, and store word have 2 register operands and an immediate or constant. So we still, though, keep the number of instruction formats small. So we have our essentially our 4 instruction formats, and 2 of those have kind of variations on them. But instead of having 20 instruction formats, which now will make our hardware a lot harder, right? If you have someone turning in some form and there are 30 different versions of it, it's going to take a lot more work to have to deal with that form or to have to process that form. Same thing here. If we keep the number of instruction formats small to still have a simpler design because of that, regularity, and smaller is faster.